Okay, welcome to Let's Get to the Marks, going through the GCSE Combined Science Trilogy. This is the Chemistry Paper 2, 2021. It looks like there are 6 questions. You've got an hour and 15 minutes. What I suggest is you pause the video at the start of each question, have a read through, have a go on scrap paper with a pen, use your calculator, make the revision active, then unpause and watch the walkthrough. So a student investigated the reaction between magnesium and excess hydrochloric acid. Figure 1 shows all the apparatus. This is the method they used. Pour 50 centimeter cubed of hydrochloric acid into a conical flask, add a piece of magnesium, insert a stopper and delivery tube and start a timer. Collect the gas produced in the gas syringe. Record the volume of gas every 20 seconds for 2 minutes. Repeat steps 1 to 5 at higher concentrations of hydrochloric acid. And then it says give the independent variable and one control variable. So the independent variable is the thing that you change. And so it's normally towards the end of the method, but it says they repeated using different concentrations of acid. So that's the independent variable. If we look at the control variable, it's what did they keep the same? The only thing I can see that they kept the same here is the 50 centimeter cubed of hydrochloric acid. So that's the volume. We could say they kept the mass of the magnesium the same or the surface area, but they specifically talked about the volume of hydrochloric acid. Okay, for this question, they want us to complete figure 2. We've got to plot the points from the table, naught's done for us, and then draw a line of best fit. And so we're going to use these numbers from this table and put them on here. And I'm just going to show you how to do that. And so your first dot here, we're going up here. It looks like the value is 20, 10 squares. So you do 20 divided by 10. You can work out that each little square is worth 2 on the y-axis, which is the vertical axis going up the side. Each baby square is worth 2. So let's look at this second one. It's at 40 seconds along the bottom and 72. So go up to 70 and then just one square up makes 72. And then 60 and 90. Nice and easy, that one, because it's bang on the lines. 60 and 90 is in between 80 and 100 on the y-axis. And then 80 seconds along the bottom and 97. So we just want to count up 6. This is a difficult one when it's an odd number on these because they've got to go in between, in the middle of a square, basically. But you're allowed to be half a square out. So don't panic if you feel like you've gone over the line, because you're allowed to be half a baby square out and they will give you the plot. Okay, you get 2 marks for the plots and then a curve of best fit here. You should see that this is naturally a curve of best fit. And if you're doing this on paper, you don't take your pen off the paper. You do a smooth curve through all the dots, like so. And you don't join the dots up. If you miss one dot, you miss one dot. Don't join the dots up with your curve. And that's worth 3 marks. Now, 1.3, how does the rate of this reaction change with time? Have a think about that. So what happens to the speed of the reaction over time? Think about the shape of the graph we just drew. You might want to pause the video, try and see if you can work out the answer. The answer is that the rate decreases. Why does the rate go down? Why does the speed of reaction slow down? Well, if you look at our graph, look, when is it going fastest? You've got time at the bottom and rate on the side. You can see the rate is increasing the most at the start of the reaction. That's where you've got the steepest line. Towards the end of the reaction, it's leveled off and the rate has become, well, 0. Rate hasn't become 0, but it hasn't got any faster. And that's because our reactants have run out. So a student repeated the experiment using hydrochloric acid with a higher conc. What's going to happen if you have a higher concentration? Well, a catalyst lowers the activation energy. Concentration doesn't change that. And the magnesium reacted more quickly. Well, yeah, if you have a higher concentration, we would expect the reactants to react more quickly. The reaction finished at the same time. What, a higher concentration, you're going to get more particle collisions. It's going to change the time of the reaction. And you're going to get a greater volume of gas released if you have a higher concentration, because it means you're going to have more particles. Right, 1.5, temperature also affects the rate of reaction. Explain how increasing the temperature affects the rate of reaction. Refer to particles and collisions. So you've got 2 sets of reactant particles. What happens when you make them hotter? Why don't you pause the video, have a go at this? So as we increase the temperature, those particles are going to gain energy. What type of energy? Kinetic energy. They're going to move faster, bang into each other faster, and more chance of them colliding because they're moving faster. So you've increased the probability of a collision, more frequent collisions. But you've also, because they have more energy, the collisions are going to be harder and more energetic. And that means they're more likely to have energy above the activation energy and be successful. So increasing the temperature not only increases the kinetic energy and speed of the particles and therefore more frequent collisions, it also increases the chance of the collision being what we call successful. A successful collision is where they can collide with enough energy that it's greater than the minimum energy to break bonds, which is called the activation energy. So it's more likely they'll collide, but it's also more likely that they'll collide harder with enough energy for a reaction to happen. So we're going to get 3 marks here, one for saying they move faster or have more kinetic energy, one for saying more frequent collisions, and one for saying more successful collisions. Okay, let's move on to the next question. Right, question 2. Crude oil is a resource found in rocks. Most of the compounds in crude oil are hydrocarbons. Complete the sentence. Crude oil is formed by the decomposition of what breaks down to make the black, thick, liquid mixture that's crude oil. And it's marine life, things that live in the sea, especially from millions of years ago. It's plankton. And this happened hundreds of millions of years ago. They decomposed with heat and pressure under specific conditions, anaerobic conditions, to create crude oil. Now, name the alkane that has 3 carbon atoms. I'm drawing it out for you right here. So, which alkane am I drawing out here? You might know the name of 1 is methane, 2 is ethane, and 3 carbons is propane, and 4 is butane. There's a rhyme for that. What is it? Monkeys eat peanut butter. So, monkeys eat peanut butter tells you the 4 you've got to know: methane, ethane, propane, butane. Right, 2.3. Figure 3 shows 2 alkane molecules. We've got methane and hexane here. Hexane has 6 carbons. Table 2 shows the melting point and boiling points of methane and hexane. So you can see them here. You can compare them. Hexane has a higher melting point and a higher boiling point. Compare the structure and the properties of methane and hexane for 6 marks. So what you have to do here is you're going to get some marks for talking about the structure. So look at them physically. How can you compare them? What is the same? What is different? So what do they both have or contain, and what do they both have that is different? So that's the nice easy bit. And then you've got to link that to their properties, like their boiling point and their melting point. So how does what you see with your eyes there affect their melting and boiling point? Okay, so it's 6 marks. So why don't you pause the video, grab a pen, bit of paper, have a go and see if you can work out what's the same and what's the difference between them. All right, I'm going to go through the answers. So what's that atom there with a question mark? I've done an arrow. They both contain carbon atoms. So I would say they both contain carbon. However, methane has how many carbons? 1. Hexane has 6. So we've said a similarity and a difference. And then what else do they both contain? They both contain hydrogens, and methane has 4 and hexane has, what's that, 14, I believe so. They both contain single CH bonds. They both contain CC bonds. They both can. Oh, actually, hexane has carbon-carbon bonds, CC bonds. Methane doesn't, so that's a difference. They both contain covalent bonds. They're both hydrocarbons. Hydrocarbons are compounds that only contain carbon and hydrogen, so they're both hydrocarbons. Both have covalent bonds, but like I said, hexane's the only one with the CC bond. And then they both have CH bonds. So we're comparing the different bonds here. Which one is smaller? Which one is bigger? So methane is a smaller molecule. Hexane is a bigger molecule. So we're doing all these structural comparisons. Of course, they're both covalent compounds because they're made of non-metals. And then if we look at their properties, both of them are flammable, so can be used as fuels. I would say that methane is more flammable, as methane's a gas, right, and hexane's a liquid. So methane is more flammable. Both can burn easily because they set alight easily, right? And methane is, yeah, more easily set alight. I suppose hexane is easier for transport because it's a liquid. Gases you have to compress; they're a little bit harder to transport. Hexane is a bigger molecule and so has stronger intermolecular forces between the molecules. So those are the weak intermolecular forces in between the molecules. They're both simple molecules, simple covalent compounds, right? They're not giant structures. I know hexane looks like it has a lot of atoms, but it doesn't. It's only got like 20 atoms in one molecule. That's very small. So that's a simple molecule. It's just that methane is an even smaller simple molecule. So if you look at hexane, which I'm writing with an H here, hexane will have weak intermolecular forces between the molecules, but so will methane. And methane is even smaller than hexane. So methane will have weaker intermolecular forces, which need less energy to break, hence why methane's melting and boiling point are both lower than hexane's. Okay, so I'm drawing these little circles with an M. These are supposed to represent methane. You can see they're smaller than the hexane circles. So the methane molecules have weaker intermolecular forces, less energy required to break them, so the lower melting and boiling point. I think we've covered it all. We've covered volatility. We could say, you could use the word volatile. Viscosity. I haven't talked about viscosity. So which one is going to be thicker? Hexane, if you think of fractional distillation, it's a bigger molecule, stronger forces. It's going to be more viscous. It's going to be thicker and possibly a darker color, but I believe they're both colorless. So not much of a comparison with the colors there, but it's certainly going to be thicker and more viscous. Okay, I think that's covered about all of it. There might be a couple of extra points I've missed that would be on the mark scheme, but this would more than get you 6 marks. Well, not more than, you'll get 6 marks for all of this, definitely. And let's move on. So we're now on to 2.4. Hydrocarbons are cracked to produce more useful alkanes and alkenes. Decane, C10H22, is cracked to produce two products. Complete the equation for the reaction. Let's zoom in a little. So you've got C10H22 on the left, and you need to make sure it all adds up to C10H22 on the right. Pause the video, have a go. Okay, I'm going to show you how to do it. You go C10H22, take away what we have existing on the right, C2H4, means that we need to make up C8H18. And there we go. Easy peasy. Sometimes they're a lot more difficult than that because they might have two spaces for you to make up. Right, 2.5. C2H4 is an alkene. What is the test for alkenes? Alkenes have the general formula CNH2N, and you have to know off by heart that alkanes have the general formula CNH2N plus 2. But that's not what this question is asking. This question is saying, what's the test for the double bond for the alkenes? And the test for the double bond is to add bromine water, which is orange in color, and it decolorizes. It goes from orange to colorless, or you can say it decolorizes as the bromine adds across the double bond. Okay, question 3. The methods used to produce potable or potable water, depending on how you want to call it, depend on the available sources of water, suggest how copper sulfate can be used to test for the presence of water. Okay, so we're going to heat some copper sulfate. You might want to pause the video, see if you can do this one. If you don't know the answer to this, put it on a revision card, all right? So put the question on the front and on the back, write the answer. Heat some copper sulfate to evaporate any water and it becomes this white powder of anhydrous copper sulfate. Now, copper sulfate that's hydrated is normally blue. So when you heat it and evaporate the water, it goes white. And guess what? If you add any drops of water to the white crystal, it will turn back into blue copper sulfate. So it's a great test for seeing if you're dealing with water. Don't forget to hit the like. It massively helps out the channel. If you hit the like, it's going to help other people find my channel and watch my videos and help me and encourage me to make more videos to help you smash your exams. Okay. And you could subscribe if you like, and if you really like, you could become a member. $1.99, and you get early access to all my walkthroughs about 3 or 4 weeks before they come out, and you get access to some content that is exclusive for members only. All right, guys. The boiling point is used to check the purity of a sample of water. 3.2. In chemistry, what is meant by a pure substance? Well, a pure substance is a chemical that's only made of one compound, molecule, or element. So it's only made of one thing. E.g., pure water would only contain the compound H2O and it wouldn't contain anything else. Pure carbon dioxide would only contain CO2 molecules and it wouldn't contain anything else. And so that is going to get you 1 mark. Okay, let's move on to question 3.3. The boiling point of a 250-gram sample of water was 100.60 degrees. The boiling point of pure water in a data book is 100 degrees. Each 1% of impurity increases the boiling point of water by 0.12 degrees. Calculate the mass of impurity in the sample of water. I suggest you bust out your calculator, grab some paper, grab a pen, have a go at this one. It's one of them difficult mathematics in science, kind of mental maths. Okay, let's get into it. There aren't really any formulas you got to use for this. It's just your mental maths. I'm going to go through the explanation. Hopefully you had to go on scrap paper. So the first thing I want to do is find out the difference. I'm going to do 100.60 minus 100, and that shows that I was 0.60 degrees above, and we're told that each difference of 0.12 is equal to 1%. So if I do 0.60 divided by 0.12, I find there's a 5% difference, right? Because each 0.12 is 1%. So if I do 0.60 divided by 0.12, that tells me that there are 5 lots of 0.12, and that means that 5% of impurity. Now we just need to find out what is 5% of 250 grams. Now, one way to do this is to do 250 times 5 over 100. When you want to times by a percentage, put the percent over 100 and times the number you want to do, and that is going to give you the percent. What is 5% of 250 grams? So you could do that. You could alternatively divide 250 by 100 and you get 2.5. So 2.5 grams for a percent, and then times 5. 2.5 times 5 is 12.5. You get the same answer. So there's just different ways to get to the same answer. And there we go. That's one of their mental maths ones, just going to get you thinking on your feet, and you just need to practice, practice, practice. You'll get that practice by doing past papers and putting yourself in that situation. All right, guys, let's continue with a walkthrough. So let's look at 3.4. Explain how distillation is used to obtain potable or potable water from salty water. So distillation, this is where we're going to heat the water up. And when you heat the water up, it's going to evaporate. What's it going to turn into? It's going to turn into water vapor, which is a gas. It's going to turn into steam or water vapor. And then rather than letting that water vapor escape and leave the salt behind, we need to collect that water vapor. And we use something called a condenser. You don't have to know the specific name, but it's actually called a Liebig or Liebig condenser, named after, I guess, the guy who used it a lot in chemistry. So, yeah, it goes into this Liebig condenser where cold water runs inside the walls of the glass. And this causes the water vapor to condense by cooling it down and turning it back into a liquid. So there's some key words here for 4 marks, because it's quite a short answer really for 4 marks. You basically need to say heat the water, 1 mark, evaporate, 2 marks, cool the water, 3 marks, condense, 4 marks. So it's kind of weird. It's like heat, 1 mark, evaporate, 2 marks, then cool it, then condense it. And that will get you 4 fat, beautiful marks. So they're your key words that you need to be thinking about. And after all, science is really a game of science exams are a game of keywords. Learning the keywords that you need to think about and need to trigger in your mind when you hear certain words, like explain distillation. Every time you have to explain distillation, it's going to be heat, evaporate, cool, condense, like that. So you could do that on a revision card. You could write distillation and then on the back write heat it, evaporate it, cool it, condense it. And that would basically get the key points in your head. Right, 3.5, obtaining potable water from salty water is more expensive than potable water from groundwater. Why is that? So compare the methods. So you might want to pause and have a go. Right, potable water from groundwater. Groundwater is the kind of water when it rains, the lakes, the rivers, but it's also that's kind of surface water. Groundwater is fills in underground caverns called aqueducts as well, and essentially it's the water from the rain. And all we need to do with rainwater is filter it and then sterilize it using chlorine, ozone, or UV light. Whereas if you're going to use distillation, you're taking water from salt water from the sea. And they do this in hot countries like the United Arab Emirates, where they don't have a lot of rain. So where they don't have a lot of rain, they're going to boil the water first and evaporate it and then condense it, as we talked about earlier. And so that requires an extra step and therefore more money, because you spend money on the energy to heat and boil it. You still need to sterilize it as well, but you've got that extra step with distillation where you've got to evaporate the water to get it away from the salt. Rainwater doesn't have that level of salt in it. Okay, question 4. Industries use the Earth's natural copper resources to produce useful products. Figure 4 shows the world production of copper from 1900 to 2020, world production of copper in billions of kilograms and years along the bottom. Describe the trend. So let's have a look at this line here, right, folks? Now it's 2 marks. If it was just 1 mark, we just need to say production of copper goes up over the years and or over time, and that will get you the general trend mark. So the general trend will get you 1 mark if you just say the production of copper has increased. That's going to get you 1 mark. Copper has increased over time, and that is the general trend. And what I've circled on the graph is the more specific nuance to get you the second mark when you have to describe a graph. So what's the difference in those two parts of the graph? So we'd say the difference is the production of copper was increasing slowly, and then after about 1950 or whenever you want to say, it started to increase more rapidly. And you can tell that from the steeper line. So you just want to say the general trend is the production of copper went up slowly at first and then at a higher rate later on. Lovely, 2 marks. Okay, let's go to 4.2. Suggest one reason for the trend in figure 4. So why don't you think about it? Why would we use more copper nowadays than we used to in the past? What has changed about the earth? Why we need more copper? And any kind of point you can come up with will get you the mark here. Pause, have a think. Okay, I'm going to go through the answers. So basically the human population has increased, right? We've gone up by billions and billions in just the last 100 years, and all those people need electricity in their homes, so more electrical wiring. Most of them use copper saucepans or copper frying pans, copper for cooking utensils, copper pipes. A lot of the water that's piped into people's houses around the world is using copper pipes. And copper is used in other things as well, roofing, structural, uh, structural oh my gosh, I can't even think what I'm talking about. Anyway, stuff to build houses. 4.3. Suggest one reason why the trend cannot be accurately used to predict the future production of world copper. So we don't know how long these copper ores and the copper is going to last inside the earth. We might run out of copper. So we can't predict that we're going to use copper if it runs out. Also, what's happened is we've started to replace copper pipes in houses with plastic pipes. They're more flexible and cheaper. So we don't know what new technologies might come out that may replace copper for its uses. And also, we don't know how long copper ores or copper supplies will last. Okay, let's move on to question 4.4. High-grade copper resources are now difficult to find. Phytomining is used to extract copper from low-grade ores. There are 5 stages, A, B, C, D, and E, in phytomining. The stages are not in the correct order. Here are the 5 stages, guys. Why don't you try to put these in the correct order? A, B, C, D, E. Write it down on a bit of paper and pause and have a go. All right, I'm going to go through the answers. So, first of all, the plants are harvested. Oh, no, nope, 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 nope. First of all, we're growing the plants, and during that process, they absorb metal from the soil. Then we harvest them. That means chop them and get them out. Then we burn the plants, and from the ash, we're going to get the metal out, and we dissolve it in acid, and then we use electrolysis to get the metal ions to attract to the negative electrode. So that is the correct order, and that is BDC, 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 BDC. So it's this one, the second one, BDC, AE. I had to try and remember what that was. Okay, let's move on to the next part of the question. What we got? We got 4.5. Give 2 disadvantages of phytomining compared with traditional mining methods. Do not refer to cost. So 2 disadvantages of phytomining. Difficult. So it's going to take longer than traditional mining, because with traditional mining you just go down and smash out the metal ore out the rock, out of the rocks, out of the ground. Whereas with phytomining, you've actually got to plant the plants, allow them to grow, give them time to soak up the metal, and then you've got to burn them, mix them with the ash with the acid, and use electrolysis to extract them. Whereas You can't make enough copper this way either. So when you go down and do traditional mining, you can find rocks that contain loads and loads of copper. But phyto mining is you're only going to produce a small amount of copper. So on a small scale, you're not going to be able to meet the massive demand for copper wiring and copper pipes across the world by phyto mining alone. All right, we've got another mental maths one. Whoa, this one's difficult. 4.6 in 1 year, 8.89 times 10 to the 9 kilograms of copper was produced. 41% of this copper was produced from recycled copper. The energy to produce 1 kilogram of copper from copper ore is 70.4 megajoules. The energy needed to produce 1 kilogram of recycled copper is 27.2 megajoules. Calculate the difference in energy used if all of the copper was produced from recycling and give your answer to 3 significant figures. And this bad boy is worth 5 marks. It is a difficult one. Grab your calculator, grab your pen, pause the video, have a go, and then I'm going to go through the answer. Okay, so first up, I want to find out 41% was produced from recycled copper. So I want to find out what 41% of 8.89 times 10 to the 9 is. So I'm going to do 41 divided by 100, and I'm going to times it by 8.89 times 10 to the 9. And this is going to tell me how many kilograms of copper were made by recycling. So let's work that out. And then from the number of kilograms of copper that are made, we can times it by the energy per kilogram and work out the total energy that was used to produce copper from recycling. So we're going to find that if we do 8.89 times 10 to the 9 in the calculator, we're going to get 3644,900,000 kilograms, some big fat number. Okay, so there was a massive amount of kilograms of copper produced in this year. And this is the 41% that was made by recycling. Now I want to find out how much energy that used to make that much copper. So we're going to get 1 mark for what we've done so far, 1 mark out of 5. Now we're going to times it by 27.2 megajoules. The M, by the way, a big capital M, means it's megajoules, not millijoules. So we're going to times it by 27.2, and this is going to tell us how many megajoules was used to produce recycled copper. So it's 9.91 something or other, but I'm gonna round it to 9.91. It's like a load of other numbers, but I'm just for simplification because otherwise I've got to write it down. I suggest you should keep all the numbers if you can in your calculator so you don't round, but I'm having to round to write my working out. So 9.91 times 10 to the 10 megajoules is made from recycling. So we now know how much energy was made or used to produce copper by recycling. Now we need to add this to the energy that was used to get copper from the rocks, from the copper ore. So I've got 2 marks so far, but now I need to realize that I've got 100 minus 41, 59% of all the copper produced of the 8.89 times 10 to the 9 was produced from copper rocks. So I now need to find out how much energy was used to produce that. So I'm going to do 59 over 100 times 8.89 times 10 to the 9. So that's the mass of copper that was made from rocks. And I'm going to times that by the energy per kilogram. So I'm going to times that by 70.4 megajoules. And that is going to give me the total amount of energy used to get the copper out of the rocks. Okay. And then we're going to add these 2 numbers together and we're going to have got about 3 marks at this point. So this is a very difficult question, I ain't going to lie. So now we're going to go 3.69 times 10 to the 11 megajoules. Okay. Now the question, we're going to add that, and that is from copper ore. Now we need to do the total energy from the copper ore and the recycling. What's the total? Well, it's 9.91 times 10 to the 10. Which is the energy that was used to get copper from recycling, added to 3.69 times 10 to the 11, which is the energy used to get copper from the copper ore. And that's going to give us the total energy used that year to produce 8.89 times 10 to the 9 kilograms of copper. Okay. And let's smash that in the calc. It's 4.68 times 10 to the 11. So 4.68 times 10 to the 11 megajoules is the total amount of energy used to produce copper. Now that we know that, we have to imagine that they did 1 year, they just did it, but they or the same year they did it, but they only used recycled copper. So now what we need to do is find out how much energy would be produced if they just did recycled copper. So if they just did recycled copper, we'd do 8.89 times 10 to the 9. This is an easy bit. We just do the mass of the copper times the mass per kilogram when you recycle, the energy per kilogram, sorry. So we go 8.89 times 10 to the 9 times 27.2 megajoules. And this is going to equal the total energy if we just did recycling. And if we just did recycling, the total energy is going to be 2.4142, if we're rounding, times 10 to the 11. So about half, just over half, but a lot less energy. Now, we need to find the difference between these two numbers, and that's going to get us the fifth mark when we put that difference into three significant figures. So find the difference between 4.68 times 10 to the 11 and 2.42 times 10 to the 11. So essentially, you just want to do 4.68 minus 2.42, and you've got your answer. Okay, so 4.68 times 10 to the 11 minus 2.42 times 10 to the 11, or you could just do 4.68 minus 2.42 and that on 10 times 10 to the 11 at the end. It's up to you, really. And that is going to give us our lovely jubbly answer, which is 2.62 times 10 to the 11. And there's our difference, 2.62 times 10 to the power of 11. And because I rounded on, 2.26. Gosh, I get my numbers around the wrong way. What an idiot. Right, 2.26192 I got times 10 to the 11. Now, bear in mind, folks, so the answer is 2.26 times 10 to the 11 because we're doing it to three sig figs. You only want to show three numbers there. Bear in mind, though, that I rounded on the way when I did my 9.91 and when I did my 3.69. So on the mark scheme, the actual answer is something like 2.27 times 10 to the 11. But you just have to bear in mind that I was rounding on the way because I didn't want to write down 9.91692134789. I didn't want to put all the numbers down on the paper because I just couldn't fit it in. Okay, so in your calculator, it's best to try and keep all your working rather than rounding your working. It's best to only leave your rounding till you get your final answer, because if you round your working through one of these maths ones, your final answer is going to be slightly different than the actual answer. All right, and that's going to get you all of the marks. Question 5. Atmospheric pollution is emitted by cars. Some car emissions contain nitrogen dioxide. Describe how nitrogen dioxide, NO2, is produced in the engine of a car that burns fossil fuels. So here we have my incredible drawing of a car. I don't know what this is at the back. That's the exhaust pipe, right? Yeah. And we've got nitrogen and oxygen coming into the car engine from the air, from the atmosphere, 78% nitrogen, 21 oxygen. So we've got them coming together, and what do they form? They form nitrogen dioxide. They actually form nitrogen monoxide and trioxide and dioxide. They form all of them. Oops, I balanced that wrong. You don't really need the equation here, but it helps if you know it, so you can work out what's going on. So essentially, nitrogen and oxygen from the air come together and react. Now, why don't they do that anyway in the air? Well, it's because the metal inside a car's engine gets really, really hot, like 500 degrees or whatever. And it's hot enough that those molecules, it overcomes their activation energy and breaks them, the bonds, and they react together. So what we want to say is that nitrogen and oxygen from the air, 2 marks, react on the hot surface of the car engine or from the very high temperatures in the car to form nitrogen dioxide. And that will get us 3 marks. So it's nitrogen, oxygen from air for 2 marks, very hot, react under very hot conditions. Okay, table 3 shows the concentration of nitrogen dioxide in the air in 3 different areas for 1 week. So we've got the city centre, the countryside, and the motorway, and we've got the days, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And we've been given the concentration of nitrogen dioxide in each of those. The mean value for nitrogen dioxide in the air for the whole week in just the city centre is 33 micrograms per metre cubed. Calculate the value X for the concentration of nitrogen dioxide in the air in the city centre on Sunday. So we're missing the Sunday data just for the city centre. So we know the mean for all 7 days is 33. So what is X? Well, it's one of the values that went into making the mean. So we need to set out our equation like this. 35 plus 37 plus 37 plus 34 plus 37 plus 29 plus x. You know how to do mean from mathematics. Add them all together and then divide by the number. So we want to do all of that divided by 7. And when we divide that by 7, we know the answer is 33. So we now need to rearrange this and find what x is. Of course, there we go. We don't need to times 100. Why have I put times 100? What an idiot. Anywho, there we go. So, yeah, we don't need the times 100, folks. I think I'm having a brain meltdown. Yeah, I think I thought I was doing REM for a minute there, relative atomic mass with the old times 100. Never mind. Anyway, so how are we going to rearrange this? Well, I've got 35 plus 37 plus 37 plus 34 plus 37 plus 29. Let's add those all together to simplify this because it's quite a lot there. So if we stick them all in the calculator and add them together, we can simplify this equation that we've set out. And so what we're going to get is 209 plus x divided by 7 equals 33. Then what we want to do is get rid of the divided by 7 on the left. So what you have to do when you want to get rid of something on one side to simplify, you've got to do whatever you're going to do, you've got to do to both sides. So what I'm going to do now is I'm going to times both sides by 7. Timesing divide by 7 gets rid of the divide by 7. And that means I've got to times the 33 by 7 as well. So I end up with 209 plus x is equal to 231. Now I want to get rid of the 209, and that way I've just got what x equals. So I'm going to minus, take away 209 from each side. So if I take away 209 from 209 plus x, I just end up with x. So I'm going to have x equals 231 minus 209, and 231 minus 209 is 22. And so x is 22. And there we go. Lovely jubbly. All done. Okay, so lovely jubbly, x equals 22, and of course that's meters cubed, and that is the concentration of nitrogen dioxide in the air in the city centre on the Sunday, so the missing number. Well, let's go on to the next part to the question, 5.3. Each value in table 3 has an uncertainty of plus 2 micrograms per meter cubed. Explain why this uncertainty is most significant for the countryside data. So what this means is there is a level of uncertainty in all of these measurements, and it's plus or minus 2. But when you look at the countryside data, this has a bigger impact. Why is it? Well, it's because the countryside data is smaller. So if you have 2 as your error out of a smaller number, it's a bigger percentage, and I'm going to show you how that works out. So an uncertainty of plus or minus 2 means that this data here on the Monday, 8 for the countryside, could be 10 or it could be 6. It could be 2 up or 2 down. And that means that there's a 25% error because 2 divided by 8 times 100 is 25. Whereas we look at the city centre, it could be 35, it could go up to 37, or it could be as low as 33, the error. So you do 2 over 35 times 100, and it's only 5.71% out. The possibility of it not being right is 5.1%, basically, or 5.71%. Well, whatever. I'm waffling. Nitrogen dioxide is removed from car emissions by catalytic converters. In a catalytic converter, nitrogen dioxide reacts to produce nitrogen and oxygen. Complete the equation for the reaction. I already did this earlier with the whole car drawing. So it's basically the same thing. I've got 2 nitrogens, but 2 times O2 means I've got 4 oxygens, so I've got to balance it correctly. There we go. The catalyst in a catalytic converter contains platinum. That's a transition metal. Platinum is a finite resource. What is meant by a finite resource? So it's not infinite, it's finite or finite. It's not infinite or infinite. So it's going to run out. You might have heard of when we say infinite, meaning it will never run out. Well, finite means it's going to run out. So, yeah, there's no more of it being made by the Earth. 5.6, emissions from cars contain carbon dioxide. Explain why carbon dioxide emissions during use, so when you're driving the car, and operation, are not the total carbon footprint of the car. So we don't just look at how much carbon dioxide comes out of a car when you drive it around. we have to refer to all the stages of the life cycle assessment known as the LCA of the car. So we've got to think about, you might want to pause the video, have a go at this. All right, I'm going to go through the answers. So what we have to think about is, where did the materials come from the car? Well, we had to mine them and dig them out of the ground. And when we mine them and dig them out of the ground, the machines that do that release carbon dioxide, or they use electricity, which releases carbon dioxide in power stations. So there's the mining the materials cost. Then there's the transport cost, taking the materials to the factory or the cars to the shop. All of the transportation, lorries and vans and big vehicles that carry them, ships across the ocean, release carbon dioxide or use energy which releases carbon dioxide from power stations. So we've got that problem. We've then got inside the factory, when the car's being assembled, when the metals are being put together and the tires and the wheels, machines are using electricity or energy to do this, and this is going to release carbon dioxide unless they're completely um, supplied with green energy, which is not going to be the case. So, and then when the cars are broken down and they're disposed of, when you finished with your old car and it has to be smashed up and broken down into pieces, that process requires energy, which is going to release carbon dioxide too. What happens to the natural parts, wood that's in a car? I know not a lot of cars have wood now, but the rubber and the wood are natural materials. They may get broken down by bacteria over time and decompose and decay and release carbon dioxide. Or what happens when we have to melt the glass down to recycle it? Well, that's using energy again, releasing carbon dioxide. So lots of different ways that carbon dioxide is released in this process. Maybe some of the parts are put in landfill and all of that kind of stuff. So yeah, we have to take the impact is in getting the raw materials, part of the life cycle assessment of your mobile phone or any bit of technology or bit of equipment or product you have. And then you've got transport costs, you've got assembly costs in the factory, and then you've got disposal costs when you get rid of something. So all of those we have to take into account when we look at the carbon footprint. Anywho, ammonia is produced when a mixture of nitrogen and hydrogen reacts. The equation for the reaction is N2 gaseous plus 3 hydrogen molecules gaseous makes 2 ammonia molecules gaseous. Nitrogen is obtained from the air. The mixture of nitrogen and hydrogen must not contain carbon dioxide and oxygen. Explain how a sample can be tested to show CO2 is not present. You know the test. Easy peasy. Use lime water. It will turn cloudy if carbon dioxide is present. If you don't know your test, get a revision card, and you need to know off by heart the test for oxygen, carbon dioxide, hydrogen, and chlorine. And you need to know those 4 gas tests. A catalyst is used in the reaction. Explain how a catalyst increases the rate of reaction. Well, a catalyst lowers the activation energy by providing an alternative route or pathway for reactants to get together. And yeah, so that's the minimum energy for reactants to come together and react. The equation for the reaction to produce ammonia is repeated here. Thank you all. The reaction reaches equilibrium. Explain how an equilibrium is reached. So an equilibrium can only be reached in a closed system where you can't add product or take away reactant, where nothing can come in or nothing can go out. Basically a beaker with a lid on, right? So stuff can't get in and stuff can't get out. And it reaches equilibrium once the forwards reaction is equal to the backwards reaction. So it means the same amount of product is being produced as the same amount of product is broken down. So the product levels do not change at equilibrium, and the reactant levels do not change, because the same amount of reactant is becoming product as product is becoming reactant. Okay, that's worth 2 marks. Big misconception there is people say you have the same amount of product and reactant. You don't. The amounts don't change, but it doesn't mean that they're equal. Right, suggest how the catalyst affects the equilibrium position. Right, a catalyst does not have an effect on equilibrium position. A catalyst purely speeds up the amount of time it takes to reach equilibrium by speeding up the forward and backward reaction by the same amount. So because it might double the speed of the forward reaction, it will therefore double the speed of the backward reaction. So it does not affect the position of equilibrium. The reaction rates, the forward and backward reaction rates, stay the same. Well, they're both equal to each other. They just get faster, but they both get faster by the same amount, so it doesn't affect the position. What is the effect of increasing pressure on the reaction to produce ammonia? Well, let's have a look. When you're looking at pressure, you have to look at how many gas molecules are on either side of the reversible symbol. So I've got 2 gas molecules on the right, and I've got 4 gas molecules on the left. Now, if you can't work that out, I'm going to show you visually how. You've got 1 nitrogen molecule, and you've got 3 hydrogen molecule, 3 H2s. Okay, and these are separate particles. Yes, they're joined together with a bond, and we could show the atoms, but I'm simplifying it. We've also got 2 NH3 molecules. So that's only 2 on the right, and it's 4 on the left. I know that can be confusing because you can look at the big numbers, the coefficients, and the little numbers. But so, which side has more pressure? Well, the 4 particles are going to collide more and have more pressure, and the 2 particles have got less pressure. So if you increase the pressure, Le Chatelier says it's going to oppose the change. So it's going to move to the side with the least pressure. So it's going to move to the right. And that is going to increase the yield of ammonia. We're going to get more ammonia if we do it at high pressure because it wants to shift to the right to try and reduce the particles and reduce the pressure. Now, the Ford reaction is exothermic. Explain the effect of increasing temperature on the amount or the yield of ammonia. Yield means the amount. So the right-hand side is exothermic. Let's not do that in blue because that can kind of be confusing because blue is like a cold color. So I'm going to write it in red. The right-hand side, they've told us the Ford reaction is exothermic. Now, I like to think of exothermic as hot, but you mustn't use that word in the exam. And the same way I think of endothermic, blue, cold, but don't use the word cold in the exam. Okay, but it helps when you're doing Le Chatelier's principle. If we increase the temperature, Le Chatelier said the reaction will do the opposite, will oppose the change. So if we increase the temperature, the reaction will say, no, I'm going to make it cold now, and it will shift to the left, to the endothermic cold side. What's that going to do to the amount of ammonia, the amount of NH3? It's going to decrease it because the reaction is going to shift to the cold side. So if you make it hot, it will go to the cold side, but you can't use the word cold in the exam. You've got to say endothermic. Okay. I like to think of hot and cold with temperature because it helps me understand which way it's going to shift. If we lowered the temperature, if we made the temperature less, Le Chatelier says it's going to move to the hot side. The reaction will do the opposite, and that would increase the amount of ammonia. Well, so what we want to put here is our answer. We're going to get a smaller amount or a smaller yield of ammonia because the reaction will shift to the endothermic cold side. So if you increase the temperature, the equilibrium position will shift to the left, or you can say backwards, or you can say to the endothermic side. And this is because Le Chatelier says it was trying to oppose the change, which was the increase in temperature. So it shifts to the endothermic side. And this gives us less ammonia. We need to include that we will get less ammonia. The yield of ammonia will go down or decrease, and that will be all of the marks. All right, guys, thanks for watching the video. Massive helps if you hit the like. In fact, you know what I'm going to say. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you on the next chemistry walkthrough.
You're still here? It's over.